second part of chapter 6 about Heaps and Coxeter group. Last time we have seen fully commutative elements in Coxeter group, especially the symmetry group. Today we are going to learn about the temporally Lie algebra, which is strongly related to the fully commutative elements. So I just remind you what we have seen in the previous lecture. So the symmetry group is defined by these three relations with the generator, commutation, reflection, and the braid relation. The Dynkin diagram of this group is this very simple graph. So the first relation tell you that we are in the commutation monoid, visualized by heaps of pieces, heaps of dimers. To any heaps of such dimers, sometimes, sorry for the notation, sometimes it's UI equals sigma I. It's come from two different talks, and I had no time to put in harmony the notation. So to any heaps of pieces, which take account only of the first relation, second relation, sigma I the square equal identity means it's a strict heap, no two dimers one over another. And the third relation, the braid relation, it's a relation on heaps to heaps. So to any permutation, any heaps, you can associate a permutation where the dimers become generator of the symmetry group. We have the notion of reduced decomposition of a permutation when the permutation, the product of this generator is a minimum length. And then we have seen that the set of all reduced decomposition in any Coxeter group, in fact, is a Dijon union of commutation class. And for each of this commutation class, there is a heap associated with the commutation class. S is a set of generator. W is a Coxeter group. And then for each of this heap, the set of linear extension is exactly the set of all reduced decomposition associated to the heap. So to each element of the Coxeter group, there is a union of heap, a collection of heaps, and we have definition. An element of the Coxeter group W is fully commutative if and only if this class of reduced decomposition is reduced to one single commutation class. And so there is a heap behind this commutation class, which will be called also fully commutative heap. And we have seen, in the case of the symmetry group, the Coxeter algebra, Coxeter groups AN, then this is a characterization of a fully commutative heaps. First, we have to define the stair decomposition of a heap of dimers, like this. This is a unique decomposition of the heaps of dimers into stairs. This is stair, you see, it's a sequence of dimers which touch each other, like this. And this is a unique decomposition. The heaps is a union of all these Dijon stair, and then there is a total order on the stair. This is the first one, second one, third one, fourth one. This is analog of the lexicographic normal form for heaps of dimers or heaps of segments. So this was explained all this last time. And once you get this stair decomposition, then there is a characterization of fully commutative heaps, like this. Here is the stair decomposition, satisfying the two following conditions. If you take the topmost element of each stair, E1, E2, now it's E. Sometimes it's U, sometimes it's E, sometimes it's sigma. E is for temporally Lie algebra. So it's the same, E or U or sigma. So here is E1, E2, E4, you see, E8, because I'm in column generator 8, here 11, E15. So here it's in each, this is the first column, second column, third column. So in each column, you have the variable E index I, if I am in column number I. And this green element, the condition, first condition, the indices must be strictly increasing. See here it's in green, 1, 2, 4, 7, 8, 11, 15. This is the indices, 1, 2, 4, 7, 8, 11, 15. This is the indices of the topmost element of each stair. Second condition, now you take the minimum element of each stair, E2, E3, E4, E7, E12, E13, E15, then this sequence of elements must also be strictly increasing. So you have two sequences of elements, which are between 1 and n. and they are strictly increasing. And of course, because it's a minimum element and maximum element of a stair, so the blue numbers are bigger or equal to the green number. So we have this kind of pair of sequence with this inequality, strict or large inequality. Then it is well known that this is enumerated by the Catalan numbers. We have seen a bijection. There is many bijection with, but we have seen one with Dick path. So if you see, if I suppose the dimers are attracting each other, so this dimer is going to be attracted by this one like magnet, then you get this kind of a pre-heap, which is in fact a skew-Ferrer diagram, such as that. This is the row of the skew-Ferrer here, this line, 45-degree line. So the row may be empty. This row, there is no cell, but the condition, the column are non-empty. So this was the end of the previous lecture, and now we are going to have new things. There is a bijection, another bijection, between fully commutative heaps and 3-to-1 avoiding permutation. We have seen last time a bijection with Dick word. So this is another proof that the fully commutative heaps for symmetry groups are counted by Catalan number. I am going to put them in bijection with this class of permutation. So what is a 3-to-1 avoiding permutation? It means that if you have a permutation sigma, then it means there is no 3-point like this in the permutation. There is no decreasing subsequence of length 3. Decreasing subsequence means it's not necessarily consecutive element in the permutation, but you cannot find a triple like this with I less than j less than k strictly, and sigma I strictly bigger than sigma j, bigger than sigma k. You cannot find this in the permutation. And this is well known to be counted by Catalan numbers. We will see some bijection. So we cover a whole theorem of Billet, Jokush, and Stanley in 93, that there is a bijection between 3-to-1 avoiding permutation, element having only one commutation class, so this is the fully commutative elements of the symmetry group, and heaps of pieces having no, they write the proposition in terms of a generator of the symmetry group, but translated in heaps, it means there is no such factor in the heaps and no such factor in the heaps. But be careful, there is nobody here. In this column, there is nobody. This means in the language of last time that this is a convex chain. These three elements are touching each other, and there is nobody here. Also, there is nobody in this left column here. So this is an example of a fully commutative element in the symmetry group. And where is the 3-to-1 avoiding permutation? You just replace the heaps, replace each dimers by the generator of the symmetry group, and you get this beautiful permutation written in blue and in red. So you see, you start from the 1, 2, 3, 4, 5, 6, 7, 15, and then each dimers give you a transposition. So this gives you a permutation, and you see there is an increasing, the blue sequence is an increasing sequence. The red sequence is another increasing sequence, subsequence of the permutation. So there cannot be a 3 decreasing subsequence of the permutation, because 2 of the elements should be in one of the red or the blue sequence, and it's impossible. And this is a bijection between 3-to-1 avoiding permutation and heaps of pieces having this condition to be fully commutative. So if I go back to the Ferrer diagram, the skew-Ferrer, I can also write the permutation like this, associated to the fully commutative heaps. I can write it like this. So you write below 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 until 16, and above on the upper border. So you send each blue number, you send it through the row like this. You send the number here, 7 go to 7, 9 go to 9, etc. 11 go to 11. And if you read from left to right, then you get the same permutation. It's a way of writing directly this permutation in terms of the skew-Ferrer diagram. I will come back on this to make happy Hamri. You will see a small surprise about this permutation. So let's go now to temporally algebra. So it's an yes, temporally algebra. It's an algebra which is introduced in physics. It's appeared many times in physics. So usually there is a temporally algebra for each. There is an extension for each Coxeter group. It's a quotient of the Hecke algebra, but I will restrict myself to the temporally algebra related to the symmetry group only. And this is the definition of the classical temporally algebra. So here the generator, here you see why I put EI in my previous slide. The generator are E1, E2, and En with the same commutation relation as for permutation. EI, EJ equal EJ, EI if and only if the distance between the two is bigger or equal to 2. Now e to the square is not equal to 1, but it's equal to beta times EI. So there is a parameter beta in the temporally algebra. And then the analog of the braid relation for permutation is this relation, EI plus 1 EI equal EI. And EI plus 1 EI plus 1 equal EI plus 1. So the left part is like the same as the braid, but then the right part is you put the value, the letters, which appear twice on the left part. So this is the definition of the temporally algebra. It generated, there is relation and generator. It's an algebra, depending on the parameter beta. It's a scalar. For us, it's a formal variable. So this is TLN of beta. So you see an algebra, you have some expression like this, you have to multiply some polynomial, multiply by this, and then all this monomial can be reduced. For example, E3 to E3 is going to be equal to E3, and then no equal to, yes, and then you be equal to E2. You can commute E3 and E1, so you can make some commutation. You multiply like polynomial, and then you reduce the words. And you can do this in many different ways. So reducing the word, I introduce this notation. If you take any word, arbitrary word in the generator, in the free monoid generated by the EI, then this means the sequence of reduction, of rewriting. You get a certain word W bar. If you apply some rewriting and commutation. Each time you do commutation, the length of the monomial does not decrease. As soon as you do some other relation, the second decrease, you decrease by 1. The braid relation, you decrease by 2. And maybe at the end, you have a certain word which you cannot reduce anymore. It means that even if you do some commutation, you cannot reduce it anymore. So this is all the possible rewriting. When you do this rewriting, a beta appears. So you will take account of the number of times you apply this rule beta. And here is an example. I take this word. You see, and then first I make a commutation, A4, A2, I get this. Now I have A1, A2, A1, A2, A1, so this gives me A2. Then I commute A4, A2, this gives me this. E2, E2 give me E2. I commute this two, give me this. A1, A2, A1, this give me A1. Now this give me A4, so etc. So at the end, if I don't make mistake in my rewriting, I get this word and I cannot reduce anymore. Even if I do commutation, I cannot reduce it. So definition, a word will be called reduce if and only if each word of the commutation class, so commutation class is for the Cartier-Fota monoid, for the commutation monoid by the first commutation relation. Any word in the commutation class has no factor of the type of these three possible types. Which means that even if you do commutation in your word, you cannot apply any reduction. Because maybe you cannot apply reduction, but if you do one commutation, maybe you can apply again some reduction. But then you are stuck when you do any kind of commutation you do, you cannot do any more reduction. So I will call this a reduced word. And the commutation class, it's for the... Since the,
in terms of heaps,
mm-hmm.
it's the same as last.
We are going to see in terms of heaps. reduce. I have underlying this, there is a reduced Heaps. So first proposition, if you do, what happens if you do two different possible reduction, a sequence of reduction and commutation, and another sequence of reduction commutation, so you get two different words. So propositions with a certain beta, power beta. So first proposition, I equal J. Number of times you get beta will be the same in two different possible reduction. And then the two words you get are equivalent for the commutation relation. But since the beginning, working with commutation relation is better to work with heap. Because heap reduce, the whole commutation class is reduced a single element. So I rewrite this proposition in terms of heap. So you can make some rewriting directly in the heap. Means that if you have this inside the heap, this means there is nobody here. So this three element can be reduced to a single dimers. These three elements with nobody here can be reduced to this single dimers. This is EI plus 1, EI plus 1 equal EI. And then also there is this reduction. As soon as you have two dimers, one over another, you reduce it to a single dimers.
Oh, that's I plus 1.
Yes. This should be I plus 1, yes. It's the one which is repeated twice. Okay, sorry, it should be I plus 1 here. This was made on purpose, to see if you are sleeping. This is the same joke as usual, but I should not repeat this joke. So definition, the heap is reduced. The heaps of dimers on the integer is reduced. If and only if it has no factor like this. Factor means, you see, the heap can be written as a product of heaps, H prime, F, H double prime, where F is this kind of heap. This one with nobody on the left column, this one with nobody on the right column. So heap is reduced. This is equivalent to when you reduce a word, the underlying heaps is going to be reduced. So at the same time, I am working with all the words of an equivalence class. So proposition, the same as in terms of words. If you have two different rewriting of heap, giving two different heap with two different beta power I, then I equal J, it's not written, I equal J, and the two reduced heap, H1, H2, are equal. So I am going to give a proof, or at least an idea of the proof of this. There is an invariant. When I do the rewriting, yes, I equal to J. It's missing in the slides. And if the two H1, H2 are two reduced heaps, then H1 equals H2. So there is a single, only one. So this is equivalent. This has a consequence, the first proposition. When you reduce words, all the words you get are in the same equivalence class. So this consequence of this theorem, which if you reduce a heap, what you remain at the end is only a single heap, only one, which corresponds to only one commutation class for the reduced word. So to prove this proposition, I am going to associate to each heap of dimers a planar diagram. And I'm going to show that this diagram is invariant in the reduction of a heap. So here is a heaps of dimers. Any heap, not necessarily reduced, not necessarily, I can apply the reduction here. And then I am to associate a planar diagram to this. Sometimes topology algebra I call planar algebra because they can be defined by planar diagrams. So the way I'm introducing all this is totally non-classic because the main idea is heap, so it's totally non-classic way to introduce topology algebra. Usually they introduced by Kaufman generator, but I reverse completely the machinery. And starting from heaps and going to the classical definition of a planar diagram. So let's take a heap of dimers. And then you associate to each dimers. First, you associate this green line above and below the dimers. And these green lines are going up. You see, there is a little thing going up. They are waiting to put some more line. And I put some more line like this. You see, when, for example, this one, I go down, and then I touch this one, so I will join them by this one, I will go down, and then join them here, and this one, if I go down, then I go. And so you have a heap of dimers, and I associate this diagram. If we want to look, here is a diagram. So there is some loops. You recognize beta to the square. Each time there is a loop, this is a beta. And now you recognize that if you take this line, you see you go, and then you come back here. So if I was taking this green line and stretching them, I would get this. From this, you see it? For example, this lines go to this. You take all the connected components. This line, if you follow the green line, then you go like this, and here. So this green line will give this one. These two lines will give this one, and these two here, these two, and then the loops disappeared. When I go from this to this, I cancel the loop, but I keep the number of loops as a parameter beta. So you see the process. First, a heaps of dimers, then this planar diagram D of the H, and from this planar diagram you get this kind of line, which is classical interpretation of Catalan numbers, or classical interpretation of the temporally element of the temporally algebra. So what I am going to do to prove the proposition is that if I do the reduction in the word or in the heaps, then the planar diagram D of H is invariant. It's an invariant in the reduction. For example, if you do this reduction, and if you take the planar diagram, you see this planar diagram of the first left part, planar diagram of the right part, and if you look in the reduction of the planar diagram, reduction I mean going from this to this. If you just take the reduce planar diagram, which is an element counted by a Catalan number. So if you take this line, the line in left becomes this, and this too becomes this. So there is an invariant. If I do this reduction, this rewriting, this planar diagram is invariant. Same if you do this rewriting, the planar diagram is invariant. And if you do also this one, then the planar diagram is invariant if you put a beta for the loops, which is going to disappear. So now I have this planar diagram invariant in the rewriting. So to prove this proposition, it will be a consequence of the following proposition, that the reduction map, the restriction of the map to reduce heaps is a bijection. If it's a reduced heaps, then there is a bijection between reduced heaps and the planar diagram, I will mean the reduced planar diagram. There is a bijection, which means that, see, if you take, go back to this proposition, if you take two different rewriting, so you get some reduced heaps. Why they are equal? Because in the rewriting, the planar diagram is invariant. So they have the same planar diagram being reduced with the same planar diagram, so they are the same heaps because it's a bijection. The last one. I should say the reduced planar diagram, like this, you see. This is a planar diagram associated to a reduced heaps of dimers, and this is a reduced planar diagram. So see, it's an invariant, the planar diagram. This is a planar diagram, but you reduce it. I should say the reduced planar diagram.
One has loops.
Here there is loops. You get the loops out. So, but you remember the number of loops by putting beta power the number of loops. So it is the the original planar diagram, and this is the reduced, I should say, the reduced planar diagram. And the proposition, so this planar diagram, the reduced planar diagram is invariant in the rewriting of the Heaps. And I should say that the restriction, that there is a bijection between reduced Heaps and reduced planar diagram. For example, here is a reduced heap. Here is this planar diagram. This is a reduced planar diagram. So this word as a reduced heap, this is an element of the basis of the temporally libre algebra. It's a reduced word. And this is in bijection with this. So I will get every proposition will be proved. As soon as I prove there is a bijection between reduced heap and reduced planar diagram. So if you have a reduced heap, then you can get a reduced planar diagram. But how to reconstruct from the reduced planar diagram like this? How to reconstruct the heaps of dimers? So this can be done in the exercise. Give a proof of the proposition. I give the idea of the proof. So you are going to, you read from left to right. Read column by column. So in the first column, between 1 and 2, there is 2 lines crossing the first column. So we are going to make a deformation of this line and put a dimers here. So you read column by column. And you can check that each time, for example, this column, now there is 4 lines crossing the second column. And then the third column, there is 2 lines crossing, then 2 lines crossing, then 0 line crossing, then 0 lines, then 2 lines crossing, then 2, and then here 1, 2 again, here 2 again, and then here 4 lines. So each time, you see, you are going from one column to another column. The total number of lines crossing the column is even, and from one column to another, the number is increasing by 2 or decreasing by 2, or keeping invariant, which means you are going from the former heaps to add a new dimers if the number of line increased by 2, or maybe to make the column 1 dimer less than the previous column. So you just try to put some dimers, the minimum possible dimers. We are not going to put many dimers. The heaps should not be reduced. And each time you are going to put a number of dimers will be invariant from the previous column, or maybe one more, or maybe one less, or maybe the same. And you can easily see that you can reconstruct. I leave this as an exercise, a technical proof that you can reconstruct slowly the heap from this diagram, and it will be a reduced heaps. As soon as you have one column already done with all the dimers in the good position, the green line are waiting for the next column. So then you are forced to put the new dimers or the old dimers or to delete in a certain position. You will see. It's easy to see. It's a technical, but I don't insist. It's easy to prove that you can reconstruct, for example, from this reduced planar diagram, you can get this reconstruction of the complete planar diagram. This is the reduced planar diagram. This is the full in green planar diagram, and this is the dimers, which give you, in fact, a primitive reduced heaps. And this was the heaps I get before with a skew Ferrier diagram with a 3-to-1 avoiding permutation. So I get a proof of this proposition. Now going back to the word, that if I take the reduction in terms of words, then what I get at the end is 2 words in the same equivalence class and with the same coefficient for beta. Like this one, you see, this was the first word, the big word with a big planar diagram, and then in the reduction, this diagram becomes this. And the reduced planar diagram can be this kind. And this is well known to be enumerated by Catalan numbers. The reduced planar diagram, one possible proof is the following. To make in bijection with Dick pass. So just you number them 1, 2, 3, 4, 5 from left to right at the bottom line, and then 6, 7, 8, 9, 10 on the up line, and then all these blue things are coming here. all these strange things in here. So you just make a fan, and then you get this is a dig pass, or this is a parenthesis, a well-done parenthesis, open parenthesis, close parenthesis, or in a dig pass you go up, down, down, etc. And so now I can define, in fact, the element of the temporary algebra like reduced diagram. So usually you can define the temporary algebra, the planar rotation of the temporary algebra. So this is an element of the temporary algebra. If I reduce.
In two directions. Like
Yes, two directions. Yes. So it's another way.
an involution or dig pass.
Yes. Oh, it must be a trivial involution. Just a mirror image and changing x in x bar in x. Or you cut the dig path. So another way to do the bijection is the following. This is the left. You just read the upper part. This is up. So this is the left factor of a dig path. Up, down, down. So it's a left factor of a. It's not a dig word coming back to the zero level. This will stay at the level 1. Then this is another left factor. So the two left factors of a dig path at the same length and finish at the same level. So if you take one of the, so this is a pair of left factor, which can be seen as a pair of standard Young tableau of height at most 2. We will see in the next slide relation with Young tableau and of height at most 2, and the pair of Young tableau of height at most 2 is exactly in the RSK correspondence, the number of 3 to 1 avoiding permutation. This is another way to see the Catalan number. So reduced diagram, like this, which is an element of the temporary algebra. So you can multiply them. It's just by putting them like this. So this is a product of two elements, of two reduced elements in the temporary algebra. You have one element above, another element below, and you just connect. Say you follow the green line, like this, you follow, and this is exactly the product of two elements. This is corresponds to the products of the reduced heaps.
What goes below and what goes above?
Or for example, this is a product of one element, first element multiplied by this one. It's not commutative. It's not commutative product. And then if you connect the green line and you stretch them to have a reduced diagram, you get this. So you see the product of this by this, and you have now some loops appearing. So the product of these two reduced elements is going to be beta the square multiplied by this element. So this is another definition of the product in the temporary algebra of reduced elements.
You take the lower one to the first in the product.
As you like. I was taking this one multiplied by this one. So first this one and then this one. Yes. Okay. In the heaps, I should take I should take this one multiplied by this one. Okay. In the term of heaps, this is below. The heaps is below this one, and then the heaps is going to be a product of two heaps. You have to reduce the heaps, and reducing the heaps correspond to reducing the planar diagram, as is done here. See this long line coming here, give you this one. So the reducing the planar diagram corresponds to reduce the heaps of dimers by the reduction defined by the generator and relation. And also taking off the loops means you keep only this beta to the square. And so this kind of product, you can now define, another way to define temporary algebra is by the classical and well-known Kaufman generator. So there is some, the reduced diagram related to each of the generator, E1, E2, En, is exactly this. EI, it's only one dimer here, EI. So you have this planar diagram related to EI. And you can see, if you take the square of EI, you have the square of EI is going to be beta EI. because the loops is going to be deleted and it's going to be exactly the same as this. Now the commutation relation EI, EJ equal EJ, EI, if and only if the distance between I and j is bigger or equal to 2, it's obvious in the term of the planar diagram. So this was relation 1 in my notation, this was relation 2, and now relation 3, analog of the braid relation for the symmetry group. Here is EI, EI plus 1 EI. So if I so this is EI, yes, EI, product from bottom to top, EI, EI plus 1 EI. So this green line becomes this, and it's become EI. So you have this is another way, a visualization of the relation defining the temporally algebra by commutation and generator. It's a visualization with this planar diagram, and usually people start from this, but here I start from Heaps to have a non-conventional way of looking temporally algebra. So this is this is family of planar algebra. And planar algebra is related to C-star algebra, von Neumann algebra, the braid, everything, the Jones polynomial, all this. So all very deep things related to all this. This is the starting point of there is many other planar algebra. And your colleague Sanders is a specialist of all the C-star algebra, C-star algebra, and planar algebra. And so Jones, the Jones polynomial can be defined from putting some braids and notes on this diagram. But I will keep an elementary level, just the temporally algebra for the regular symmetry group. So now I can give, in all classical book, there is some classical book on the De la Harpe, Jones, there is a very classical book giving a basis of the temporally algebra. So I can recover what is written in classical book on the basis of temporally algebra. So we'll see n mean nil temporally algebra. So for the temporally algebra, which means there is no occurrence of this Heaps, it's a strict Heaps, no occurrence of this in this. And we have seen that if there is no occurrence of this in a Heaps, it's a fully commutative Heaps from the previous chapter. So see, to find basis of the temporally algebra is the same as finding fully commutative Heaps, yes, in the symmetry group. So from the previous chapter, we know that fully commutative Heaps are exactly these Heaps. And then you can deduce immediately a basis of the temporally algebra. The basis is you have to take the product in a certain order. You have to take the product of this, the first segment, multiply by product of this, multiply product of this. So it takes the product of each element in the stair, starting from the minimum element to the maximum element. It takes the product, the stair being ordered from left to right. And here is an element of the basis. You see, so you take the first stair, you get A3, A1, then take the second stair, you get A3, A2, etc. See, for each stair, for example, this one, then you take the product of all these elements. So it's consecutive element, starting from one of the elements of the sequence, the blue sequence, going to the green sequence. So this is your usual way to define the basis of temporally algebra. You take two sequences of numbers, the blue and the green, satisfying this inequality. And then for each column, you take the product of all the E, for example, for this one, E12, E11, E10, 9 until 10, until 8. You take the product of all this. So to this pair of sequences, you associate this product, first stair, second stair, third stair, etc. So this is a classical way to see the basis of temporally algebra. And this is counted by Catalan numbers, because to each of this pair of sequences, this is a classical bijection. I have shown last time in the first part of the chapter that for each of this pair, you put a red point on this diagram. 12, for example, 12, 8, you see this point with abscissa 8 and coordinate 12. It's exactly this corresponds to this column. to each column you have a red point. They are going increasing. It's an increasing sequence, the lattice. Increasing means each time you are in a red point, you go to the next one, go to the northeast of the previous, and so you can join them by a path, which is a dig path, rotated dig path, where the red points become the valley of the dig path. See, maybe there is no sequence at all. The empty sequence. When if there is nobody, empty sequence. So this means the dig path has no red point, which means the dig path is this, reduced to this. So the empty sequence is also part of the picture. Total number of such sequences is total number of dig paths, which is Catalan number. So to any reduce heaps of dimer, I can get an element of the temporal algebra. So this was the element of the basis of before. Now this is written as a planar diagram, which gives you back this one. So the same as before, you see. So this planar diagram corresponds to the basis, correspond to this basis, this product of element of this product, which is coming from this sequence. Here you get the planar diagram. But we know that this planar diagram, or this, we have seen that this was also a skew-Ferrer diagram. So what happened of my planar diagram if I write it in the skew-Ferrer? So here is a skew-Ferrer. Each element of the skew-Ferrer is a dimers. Skew-Ferrer diagram becomes a reduced heaps of dimers. Amri seems to be dubitative about this. Take a skew-Ferrer, each cell is a dimer. So these two dimers are in dependency, they are consecutive columns. Now I replace each dimers by my green line to get a planar diagram. So you have a certain in green, a certain planar diagram that I can rewrite like this. See if you stretch, you see the wire here is go. So my green line go like this, in fact. I don't need to put the dimers into all the turn up and down, going through, following a green line. In fact, the green line can be exactly like this. So you see, you take a skew-Ferrer diagram, and you join each element of this upper border. You go straight until you reach something. Maybe you reach something of the lower border, or maybe you reach something on the upper border. In red, I put the point corresponding to each edges of the upper border. In blue, the point corresponding to each edges of the lower border. And my green line go horizontally, starting from an element of the lower or upper border, like this. I start from a red or a blue point, and then I finish maybe with a red, maybe with a blue. And then I can make friend with love RSK as an exercise, RSK in fully commutative heaps. So if you go back to this diagram, so take the upper border. You see, I am. So this is the starting point of a green line. I go up. Starting point of a green line. I go up. Now ending point of a green line. So I go down. So I go up or down. Each time following the upper border, I am starting a green line or ending a green line. So here I see I go up, down, because I am starting a green line, ending a green line, starting a green line, ending a green line. Now there is no line at all. So I am starting an empty line, so I go up again, etc. So what you get is a left factor of a dig path. And the number of times is the height of the final level is exactly the number of red point, where if you follow the green line, you don't connect. You are connecting to a point in the lower border. And you can do the same for the lower border. Like this, if you follow the point of the lower border, each time you starting a green line, you go up. Each time you're ending a green line, you go down. And so what you get is a pair of two such paths, left factor of Dick paths, which finish at the same level. Of course, if you take the mirror image of one and join him with this, you get a Dick path. This is another way to see that my reduce diagram are counted by Catalan number. So playing as was doing Emery with up and down and this should be like playing when you cut the Dick path in two, just at the middle, you get two left factor of Dick path. You can join the same level. But now this left factor can be encoded by a Young tableau. So each time you go up, you put, for example, the first two, 1, 2, 3, 1, 2. And then when I go down, means I am ending a green line, I put 1, 2, 3, I put a second line. So you follow your path. Each time you go up, you put the index 1, 2, 3, 4, 5, 6, 7. Each time you go up, you put as the first line. Each time you go down, means you are ending one of the green line, you go at the second level. So what you get is a classical way. It's an encoding of this path with a Young tableau, standard Young tableau with at most 2 rows. Because they are ending at the same level, the two Young tableaux have the same shape. So it's another way to encode my planar diagram. Now, if you go to this, we have seen that there is a bijection between this reduced diagram and 3-to-1 avoiding permutation, which is here. Now, if you apply Robinson RSK to this permutation, you get exactly the same pair. Exercise. Give a proof that if you start from a reduced Heaps, a fully commutative Heaps or reduced diagram, you can get a permutation. Apply Robinson instead, you get this pair of standard Young tableau. Go with the green line, the diagram, and apply what I have done, and I get the same pair.
Using light and shadow.
With maybe light and shadow. Exercise, play with this. And usually, to show that the pair, this 3-to-1 avoiding permutation, are encoded by RSK by a pair of this such tableau, to show that it's a Catalan numbers. Usually, the proof is this way. Your second tableau, you put it like this. You shift all the number, and then you get a tableau with 2 rows of the same length, and on 1, 2, 3 until 2n. And this is encoding a Dick path. This is a classical way to see that a pair of Young tableaux like this is counted by Catalan number by doing this. So you see, I play with all this bijection planar diagram, but this was an exercise for you want to play. Now another algebra is a nil temporally libre algebra. Sometimes it involves a nil. It's a variation of the temporally libre algebra, but instead of putting you have the same commutation relation, but then you put ei the square equals 0, and this equals 0. And so the basis is exactly the same. The basis is by monomial having no factor like this, because as soon as you have a factor like this by taking the reduction, it's cancelled. Instead of reducing, you take it away. So at the end, you have exactly the same basis, same dimension Catalan numbers, and same condition. You see, I put n TLN, nil temporally libre, same condition on the Heaps, so this is forbidden. So what is the interest to do this? It's sometimes it's involved in some paper, but the interest maybe is to have a representation of the nil temporally libre algebra on operator acting on the Young lattice. There is an important contribution by Fomin. If you have an operator U adding a cell in the Ferré diagram, another one deleting a cell in the Ferré diagram, so these two operators U and D satisfy the computational relation UD equal DU plus identity. It's a representation of the veil, the most simple veil algebra representation by adding or deleting a cell in a Ferrer diagram, and you are going to number the cell from each row, row number I plus 1, and from this representation, you can automatically get the Robinson RSK bijection. I will explain this in another class, maybe next year. This, from a representation of this quadratic algebra, you get automatically, in a certain sense, the RSK bijection. And you can apply this to other quadratic algebra, totally different. And again, getting natural bijection or canonical bijection coming from the algebra.
What is the representation of an algebra on Young?
By operator. So this can be represented, this one, the nil temporally, by adding some cell on a Young lattice. You take this diagram and you add one cell. So the U, the operator U of Fomin, this is related to what is called differential poset. When you add a cell, so means you are climbing one level in the Young lattice. The Ferrer diagram are ordered by, it's a lattice for the embedding of Ferrer diagram in another one. And the operator you go, it's a graded lattice. Okay, so I explain for the temporally algebra. So I can add now, instead of numbering, for the RSK, you are numbering the row, adding an element in the row number 1, number 2, number 3. No, now you are denoting the addition by the diagonal. So this is diagonal 1, 2, 3, 4, 5, etc. And here I am adding an element on the diagonal number I. So this is the operator VI, if it's possible. So I am numbering all the diagonal. This is a different way of numbering. For RSK, you number by the index of the row. First row, second row, third row. Now I am numbering the diagonal.
What is n?
Oh, it's an integer I sufficiently large so that it's above the lambda. Of course, an infinite number of diagonal. So let's say, let's give all the Ferrer diagram between the diagonal 1 and n. If I get this one equal to 1, this one equal to n. And diagonal number I, you can add a new cell if it's possible, because if you happen to be on the corner, you cannot add, or if you happen to be here, if you add a cell here, it's going to be like this, something here, and we should not be a Ferrer diagram. So if you taking a cell, sliding a cell here and putting here, if it's adding the Ferrer, it's again a Ferrer, so this is the operator VI. So VI of the lambda equal the one you can add a new cell on diagonal I to lambda, and if it's not a Ferrer, then it's 0.
But I is not well defined. Right?
You think of lambdas as every Ferrer diagram as a basis of some big vector space, on which is the linear operator. So you should take
But where you put your 1 is not right.
Well, it depends. I fix a diagonal somewhere, fix another diagonal n, large enough so that all the Ferrer you are going to take account are between this and this.
So it doesn't matter.
Yeah, you can make large enough so that.
Take the full Young's lattice. You only take till.
Till row
Yeah,
n,
yeah, yes. I take between 1 and n, all the Ferrer between 1 and n.
Yeah, not rows. The maximal rows.
Mm-hmm.
All the ones which are in the n cross n box.
But if
The
you
longest hook
if you put restriction, then the algebra will get messed up at the corner
the size of the
where you go out of it. It's like looking at Ferrer's diagrams in a box.
Because the nil temporary algebra has only a finite number of V1, V2, Vn, the generator.
That's the same as
I get it.
the 9.
I want to have a representation of the temporary algebra index n. N is fixed, so I have to have V1, V2, Vn. I have generator V1, V2, Vn, which is going to represent. I have E1, E2, En, the generator. The nil temporary is defined by this, E1, E2, En, and I want to replace EI by a certain operator VI, which is going to add a new cell in the Ferrer diagram, and I need to define V1, V2, Vn. So I take all the Ferrer between diagonal 1 and diagonal n.
EI squared is 0.
So VI square is 0. Yes, it's because of this.
Oh, okay.
So here is a proof
If it's an
that,
illegal addition, you say 0.
yeah, yes. here. See the definition, Vi of lambda equal the lambda added to this cell on diagonal I if the new cell you add to lambda give you again a Ferret diagram. If not, you put 0. Which means if I was adding a cell here, you see, then it's not a Ferret. Then I claim that my generator, my VI, my operator VI satisfies the nil temporally relation. VI, if we have two cells I and J on the diagonal I and J, such that the indices absolute value of I minus J is bigger or equal to 2, then they commute. And VI the square is 0. And now VI, if you can do, suppose you can do VI, then you can, suppose you can do VI plus 1, so the height is at least 2 here. Then if you do again VI, then this is not a Ferret, it's 0. Suppose you can do VI plus 1, suppose you can do VI, but you can do the 3 at the consecutive time, you cannot do the 3, it's always give you 0. So this is a kind of representation.
But there's no deletion here.
No deletion, no, just...
So you can think of every Young diagram as a word in the nil temporally.
Yes. I don't know too much if this is a lot of use. I learned this from Sergei Fomin. In the late 90s, we are working on this.
It's not seen much,
No, not so much, but it's... in this class, there is many things that are not classical. So I enjoy to give you some non-classical things. And then you can read classical books with a new eye, new point of view. Or this, you can ask, well, you can play with this if you... For good students, play with this exercise, research exercise, play with this and give some interesting consequence.
The operator U is sum over IVI, right? The one U you define.
The U in D, U, it's usually it's for the index, it's you are adding a cell at level high. You see, and because there is a subdivision UD equal minus DU equal identity, but then there is U index I, adding a cell at row number I, and D index I, deleting a cell at level I, which satisfies some relation, and then this gives a starting point to get RSK. And, so what is the question, Amri?
So so you're saying that if two words, words in the nil temporary algebra are the same, then the partition is going to be the same, right? That you get from these operations. But I guess the question is, what is the kernel of this? Maybe.
Good question. What is?
Is it faithful?
I think it's faithful.
Faithful, then you can count a lot of things.
Mm-hmm. Because let's say if you have a basis, see what happened. Starting from the empty diagram, apply a basis of the temporal libre algebra. It's the same as nil temporal libre. And apply what is the Ferret diagram you are going to get. It's from a basis. Mm-hmm. So it's what is the relationship with RSK? It's and U in D, you see, here there is no D. There is no. You are always adding in a proper way unless it's 0. Temporal libre algebra says this generator EI the square equal EI. So there is no inverse. There is no, like the permutation where there is an inverse. No, it's just a reduction of monomial to the reduced diagram, and you get something contained by Catalan numbers.
Can it be done for Young Fibonacci?
Fibonacci, maybe it's to have an analog. And then the next step is for any Coxeter group, when you have the fully commutative element, then this gives you a basis of an analog of the temporal libre algebra. So there's an extension of temporal libre algebra for the fully commutative element of related to Coxeter group. And each case there is a Weil algebra, the Eke algebra related. This is a quotient of the Eke. If you know what is the Eke algebra, it's a Q-analog of the symmetric algebra of the symmetric group. And this algebra, the temporal libre, becomes the quotient of the Eke algebra. So this is the official end of the chapter 6. Next lecture will be maybe the last chapter with 2 or 3 sessions Heaps in physics. but I will finish this session with a complement. If you know about symmetric function, the relationship with what I have said today and relation with symmetric function. So this is a complement. If you should have followed before the class. Last year there was a class on symmetric function, elementary function, and homogeneous function, and Jacobi 2D identity. So I suppose you know this. And so I am going to go fast in 10-15 minutes. Sorry for the student, but it is a complement. So it's a beautiful relationship. So let's start with the symmetry group and permutation. And then for each permutation, there is a symmetric function associated to each permutation. Sometimes it's called the Stanley symmetric function. Sometimes it's called a stable Schubert polynomial. Schubert polynomial can be defined in a very analog way. So you start from this diagram. I will use only the blue weight. You see, on this line, x4, x3. So each of this line is weighted with a variable xi. Usually there's a double variable with y, but I will only use the blue one. So in black, this is all the intersection point of this line. And then you take a choice in red, any subset U of the intersection point, like this. You take the red point, any subset of the black point. And then you can draw some line like this. So you start from, see this diagram, I keep the line here, all this line below, so it becomes this line, and I number them 1, 2, 3, 4, 5. And then the rule is that you go up, and each time there is a red point, the line are crossing. When there is no red point, it's like if there was a mirror between the two, and the line are just like a ball bumping. There is no crossing. Each time you have a red point, there is a crossing. What you get above, you see, if you follow this line number 5, you follow the line, the same color, then you get a 5 here. Or if you follow this green line 3, you get a 3. So what you get above is a permutation. So each time, I just recall, so you have this diagram, the intersection point in black, in red a choice of intersection point, and then you get a permutation, some line, and you get a permutation. And more, you get a monomial. You are putting a weight, all the red point on this line is going to be weighted x1. This will give you x1 to the square. All the point here, x2, give you x2 to the square. x3 give you 3 points, x3 to the square. And there is one red point on the line weighted x4. This gives you this. So it's for each of choice of the subset of red point, you get a monomial. You get some line, you get a monomial, and you get a permutation. Here you see the second diagram. It's the same permutation, but a different choice of red point and a different monomial. So the Stanley symmetric function is to take the sum of all this monomial, but for a restricted, there is a condition that if you take two threads of the line, the color line, they must intersect at most once. Say like take the green and the red line, so they intersect here, but there is no more intersection. I am supposing that my red point are such that two color lines of different color intersect at most once. So it takes the sum of all the weight, all the monomial associated to each of these subset U, takes the sum of all this monomial with the condition star, no two threads intersect, at most, they intersect at most once, and you get the summation over all such a U giving the permutation sigma. Like this, you see. Suppose you take all such a diagram, all choice of red point, such as that two color line intersect at most once. Each of these subset U give you a monomial, take the sum of all the monomial, giving a fixed permutation. And this is F sigma. F sigma, the sum of all the weight is the product of all the xi, all the monomial, sum of all subset U, giving the same permutation sigma with a condition star.
But you started with this shape.
Yes, that's the rule.
Then
It's fixed. The shape is fixed. Yes. I start from this.
This shape is
I am going to work with permutation of given size. So here the size, here the 1, 2, 3, 4, 5. This is permutation of size 5 with variable x1, x2, x3, x4. You fix the here is n and m. You fix the total number of variable x1, x2, xm, and you fix the size of the permutation. So if this fixes the diagram, this fixes the black point. Number of black point is n multiplied by m. No, minus, it's n minus 1 multiplied by m. Here there is 4 points for 5. For 5 permutation on 5 elements. In each of this line there is 4 points. And there is 4 variables. So you fix its shape, and then you get this function f sigma. And the condition star, it reminds you something of last chapter, of last time. It's to have a reduced decomposition of the permutation. So you remember here, this point, this line crossing in the diagram. Here, this line is really an analog of this line, which we are not zigzagging. So this is an analog of this line. And here, you have this permutation 4, 5, 1, 3, 2. It's a product of elementary generator. This is the exchanging 4 and 5. This is exchanging the line number 3 with line number 4. Each of these red points corresponds to a dimer or a generator. And it's exchanging, when you read from left to right, each of these red points is exchanging. You number the line. This is first line, second, third, fourth, fifth. And this line is exchanging line number, the second and third line. So you get decomposition of the permutation as a product of generator, exchanging consecutive line. But the fact that it's not a reduced decomposition here is because you see these two lines, the blue and the purple, they intersect twice. And it's easy to see that intersection more than once give you non-reduced, is equivalent to non-reduced, because you see when you can move this line, like in the Redmaster movement of knot theory, you can move this line, and each time the line goes through a red point, this is a triple intersection, this is a braid relation. And if you move the line, you see, so this blue-purple line is going to be here, and then you have two consecutive points. We have ui to the square, which is reduced by 1. So it's not reduced decomposition. This is, remind you, this star condition, remind you of to get a reduced decomposition. So now I continue the complement. What is the relationship with what we have done today? Relationship, symmetric function and 3-to-1 avoiding permutation. So proposition, if sigma is a 3-to-1 avoiding permutation, as we have seen here, it's a basis of the temporal algebra, then the symmetric function related to the permutation, exactly the symmetric function related to the skew-Ferrer. And S, skew-Ferrer, this is the sure function. To any Ferrer diagram, you can associate the sure function, Ferrer or skew-Ferrer. The sure function is defined like this. This is my skew-Ferrer, which is a reduced Heaps in the temporal algebra. This is my skew-Ferrer. So you see, you put some numbers. You have to read the skew-Ferrer is 45 degrees. So in each row, the number go increasing weakly, and each column, they go strictly increasing. So you put these numbers. This is a skew-Ferrer tableau now. A Young tableau skew-Ferrer with weakly increasing in row, strictly increasing in column. And what is the sure function related to this? To each value, each index, like 2, you replace 2 by x index 2. X number, you replace them by a variable. Take the product of all the variables, you get a monomial. And take till the sum of all this monomial for a given shape, a given skew shape. And you have to fix x1, x2, you have to fix the m. Fix the size of the monomial, you go variable x1, x2, xm, and you take all possible filling of the skew-Ferrer, fixed skew-Ferrer, with strictly increasing in row, strictly weakly increasing in row, strictly in column. You take the sum of all this monomial, and you get what is called the skew-Ferrer the sure function associated to the skew Ferrer. And I claim that this sure function is exactly the F sigma for sigma. So can we go back to the... It's exactly this sigma, this function associated in the case of permutation, which is 3-to-1 avoiding. It's because there is a bijection between 3-to-1 avoiding permutation and skew Ferrer. Or there is a bijection between this subset U configuration of resolved set and the pre-heap. So there is a bijection, I repeat, a bijection between 3-to-1 avoiding permutation and bijection with skew Ferrer. This is what we have seen today, that the skew Ferrer with non-empty column are exactly in bijection with the reduced heaps or with the fully commutative element, which are in bijection with 3-to-1 permutation. And from this, there is now a bijection, which is a tableau. The tableau itself of shape lambda, the Young tableau with skew Ferrer shape, is in bijection with the U, the set U, giving, and to seize it, you have to lift the heaps into a pre-heaps, like this. Take the skew Ferrer with the filling of the skew Ferrer, take the heaps of dimers related to this fully commutative element, and then lift it. So from this, you can lift the heaps. So this is the same. This is a pre-heap equivalent to the heap here. If all the dimers fall down, they will fall down on this heap. But now you see, I am a pre-heap, and in each of this row here, I have the value x1, x2, x3. So you see this diagram, I have to put all these dimers here. I have to put them at the level of x1. Then I put this dimer 2 at the level of x2. So each of these cells correspond to dimers. You lift them as a pre-heap so that the value here becomes exactly the diagonal number x1, number x2, x3, x4, etc. So you lift these heaps to get this and to get exactly the good value, x1, x2, x3, etc. So this pre-heap here would be in bijection with the Young tableau, the previous skew Young tableau. So this is in bijection with the skew, the tableau of before. This one, this tableau, Young tableau, is in bijection with this pre-heap and giving the same value for the monomial. And then you associate the permutation, which is the same as this one. And that's the proof, the idea, visual proof of the proposition. This gives you an idea of the proof of this. And I will finish with this beautiful following property. That now if you look the permutation, there is a blue line and green line. So I can distinguish my network of lines, the blue and the green, which are like this. Now if I rotate 45 degrees this, I get this. And this, if you follow the class of last year, this is exactly, you have the two configurations in blue and red of the Jacobi-Trudy identities. So what is Jacobi-Trudy identities? Chapter 5b, page 12 to 41. This is one of the configurations of this. And this configuration, by the LGV lemma, is an explanation of this determinant of homogeneous function. Each term of this determinant is a sum of the weight of some path. This is a homogeneous symmetric function are interpreted by this. And this determinant becomes this. And now for elementary symmetric function, there is an analog determinant, an analog configuration. See, this is now elementary symmetric function. I go very fast, but go back to the chapter, everything is explained. If I put together the two configurations, I claim that one configuration is a dual of the other. What means dual? It means that if you take this path here, it's a dual of the path, you have a kind of spanning net like this. And you see, suppose I have this is a spider net, and here I make a hole here. And in the LGV determinant, then you have a propagation of the hole, which gives you an encoding of the red path. So the red path, like this, is a dual of the blue path, which were here. So there is a kind of duality of paths. And this is exactly the two dual configuration, one over another. If I rotate them like this, if I make trembling the path, I get this, which is the Fomin definition of F sigma. So you see from this, you have this, you get this, which is the superposition of the two Jacobi identities. So the conclusion of this complement is that Fomin-Kirillov for 3-to-1 avoiding permutation equal Jacobi true D plus dual true D Jacobi with LGB lemma.
Okay. So Fomin-Kirillov is
The construction, Fomin-Kirillov is a construction like this. They have defined this construction. And if the shape is, if you cut the upper part, you get exactly the famous Schubert polynomial. So this construction line like this gives you the Schubert, this is part of the Schubert, the stable Schubert, the F sigma. And in the case, you see, in the case of the 3-to-1 avoiding permutation, in that case, then you get, this is equivalent to get this, which is a superposition of the two Jacobi true D identity for symmetric, homogeneous symmetric function and elementary symmetric function. So it's a funny observation that superposing the two Jacobi configuration, explaining the two Jacobi identity for homogeneous and elementary symmetric function, superposing these two configurations up to a slight modification of the path, you get the construction of Fomin-Kirillov in the case of 3-to-1 avoiding permutation, which is a skew-Ferret diagram.
So it may be interesting because there's a duality in symmetric functions which interchanges elementary and complete,
Yes.
and then it takes S lambda to S lambda conjugate. So
Yeah,
maybe you can
this-
prove that.
Yes, probably. Because it's exactly the dual. Yes, the dual. This duality is a. And this duality is a blue and red line in the 3-to-1 avoiding permutation. And this is correspond to fully. So this is a beautiful conclusion of the all this story of the fully commutative element in terms of the for the symmetric group. Maybe there is analog in the some other for Cn, Dn, Fn. I don't know. Maybe there are analog of this. Cn, maybe it's an analog of all this. Maybe I don't know too much. Okay, so I think we can conclude. Okay, thank you very much.